Hi, my name is Carolyn Cashman, and today I'll be talking about black hole Zeckendorf games. This work was done in collaboration with Daeyoung Sun and Jenna Shuffleton as part of the Small 2024 REU, and I was advised by Professor Ge at William and Mary as well as Professor Miller at Williams College. So for a little background information, this game is focused on the Fibonacci numbers, which are just a sequence of numbers that come from adding the two numbers before it. So 1 plus 1 is 2, 1 plus 2 is 3, etc. And the Zeckendorf decomposition is just the fact that any integer can be decomposed into non-adjacent Fibonacci numbers. So for example, 1693 is 1597 plus 89 plus 5 plus 2. So the original Zeckendorf game, which came about in about 2018, is a two-player game in which players start with an integer and then they kind of race to reach the Zeckendorf decomposition by either adding adjacent numbers or splitting one number into two Fibonacci numbers. And then the last player to move wins. And so this work was done by Professor Miller and his collaborators, and they were able to prove that player two always has a winning strategy. But this is a non-constructive proof, so it comes from assuming that player one has a winning strategy and then showing that player two later has the option to steal it. This is kind of player one's winning strategy here. But then player two is able to steal it down here. And so we considered a variation of this game, which was the black hole game. So once pieces reach a certain column, they're permanently removed, which means that we can always reduce the game to a simpler state that's a little easier to solve. We also considered an empty board game, where players start by placing n pieces in the outermost columns until the weighted sum is n, and then we start that decomposition phase of the game. And so we were able to come up with a constructive solution for this, which was super exciting, which was this, which I'm sure everyone would have guessed. It was definitely a little bit funky. But basically, it's based off of the equivalence class of both A and C for a game with the black hole on F4, which is equal to 5. And basically, it just depends on what both of those values are divisible by. So whether they're divisible by 3 or 4, or then if you subtract a certain value from them, are they now divisible by 3 or 4? And then we were also able to solve the empty board game, which once again has a bunch of exceptions, which was kind of fun. Yeah, and then so moving on, our methods, we started by trying to solve the A00 game, and we just did a pretty basic inductive proof. So we were able to show that if you have any game A00, you can reduce it down to another game that's of the form A00. And this works for everything where A isn't 2, because in 2, the player is able to move just to 1 there, and then they're done. Similarly, we were able to show that this is a player 2 win. We were also able to show that player 1 always wins if everything's in C, because you've got this 1, 0 C term right here, and then they're able to reduce down again. And this works for all C not equal to 0, 1, or 5. However, these exceptions come into a lot more play later in the game, so they tend to kind of balloon out, which is why we had those kind of crazy modular arithmetic based solutions earlier. So what we ended up doing is using a non-constructive proof again, because going back to that table, we were able to construct a proof by showing you go from winning strategy to winning strategy, but that's not very helpful unless we can actually show that those certain winning positions do win. And so our first step in doing this was to assume, as in this table here, we show that this table that player 1 is able to win, but we do this by assuming that player 2 wins, which means that no matter what player 1 does, player 2 has a winning strategy. So suppose player 1 goes here in the red, then player 2 can either go here or here. But if they were to go here, then player 1 had the option to do that before, so therefore they've got to go there. And then this game kind of repeats down until we get to this low case where this first term is going to end up being 0, and we're able to show that player 1 actually has the winning strategy there as well. So it's a little bit of a proof by contradiction. Yeah, so then just moving on, these are the two original papers right here if you want to read more about it. And then our current paper is not yet posted on the archive, but hopefully will be by the time of the symposium. So feel free to give a look for it. And if not, please email me at cecashman@wm.edu. I love talking about this and would love to talk about it more. Thank you so much for your time.